Hello.
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 Oh, Matthew, now you get, I hear your voice now.
Yes.
You get is your computer fixed?
No, I got a headset with a microphone.
Ah,
So,
you get a headset with microphone.
yeah,
Okay.
yeah.
Okay, I see Flying now. I see Ray. I think we're missing one more person, right?
Yes, we are.
Ian. So how you guys doing? Oh, weekend.
Good.
Good.
You are doing good, doing well. Did you have some other class?
Yeah.
Yeah.
Did that go well?
It was a little weird at first.
Went all
but
right.
yeah, it's actually pretty convenient, honestly. I made a sandwich in the middle of class and didn't lose any information.
That's a good sense. What class you had on this? Which large class you had?
Oh, it was English. So, but like nobody talked. So like.
Oh, so nobody talked.
Yeah, essentially.
Okay, it's similar with other larger class. Is everybody just zooming and then just listen and they automatically mute everybody?
Yeah.
Yeah.
Okay, I see Seeing, you there? Can you hear us? I think either. Let's see. Can I think the message? Where's the message go? Okay. Does the message pop up somewhere? Oh, okay, yes.
Yes.
All right, so we can't hear you. I guess it's, well, we can't hear you, but he said he can hear us. So now what I'm gonna do is I should share my screen. I should share my screen. And screen I want to share, this is one screen. Okay, there's one screen, and I should share another screen. You share, where's this one? Are you able to see me switching back and forwards between two screens?
Yes.
So this is Jupyter Lab, and this is a PDF file.
No, we can't see the PDF file.
So again, last time we went through this same problem, and there seemed to be now
Yes.
now PDF file, but the question is whether you were able to switch back and forwards or not. How about Jupyter?
Nope.
No.
So I don't remember what I did the last time. It's a new share screen. Share. What about now?
Yes.
Now we got the Jupyter.
Now you got
And
Jupyter.
Yep, now we can
Yes.
see it.
Yeah.
Okay. All right. Okay, so let's let me move this window to other place. somewhere here. And let's continue off. Just a note, I post now the homework for chapter 10, namely for the mapping part. So I think it's assignment number 9. I hope you're all able to see it. And then there is a homework due today, supposed to be. Are you guys okay with that? Or you need some more time?
That'll probably be fine.
Fine for you? Okay,
Yeah.
so let me see. Logging into my Sakai. So the homework 9 is, at least on my screen, is set online now. Homework 8, which is the one supposed to deal, so far I only have 1 people, okay, hand it in. If you guys need the extension, you need to let me know, all right?
Can I actually submit by like tomorrow? Because I have another homework today.
I can do that.
Yeah, tomorrow should be fine for me.
What about the other people?
Oh, I just realized it's today. I thought it's Thursday.
So should I just move to Thursday? I can move to Thursday, okay? How about that?
That's fine.
I'll just move the due date to Thursday, okay? And now I all weekend I play with YouTube. It took me a long time to figure out how to do this YouTube, but I think I eventually upload 2 previous lecture to YouTube, but I haven't made the link yet. I will send you guys a link. See, I just want to test out to see how things work. But you're able to see the recording properly. I mean, unlikely you're going to watch the whole thing again, because it's not much a point. But it just, in case you zoom out in the middle of the lecture and they just want to go back for clarification.
You know us so well.
Okay. So I think we end up somewhere here. We talk about Liouville's exponents. Now remember how we define Liouville's exponents? Anybody give me a what Liouville's exponents measure? Anybody want to chime in?
It's a measure of chaos depending on like a small deviation from like a given starting point, and like if it's a positive exponent, it should diverge further with time. So it's something of a numerical method of quantifying chaos.
Okay, so it's a numerical value which quantify chaos. So what value of lambda showing the attractor is chaotic?
It should be positive, right?
Yes, positive is chaotic. That's right.
Well, it's greater than 1 with maps, though, right?
Brian, try again.
Like in like continuous time, it's positive, but in discrete time, it's greater than 1, right?
No. Now here again, it's a quantitative measure of Liouville's exponents. Right? We choose a x naught, which is about in the attractor. We make a small deviation away from it, and then we iterate whether it's a map or whether it's continuous time. It's okay. So if it's, then we measure deviation after nth iteration. If it is a continuous variable, we can actually measure this. N will be time. So we say measured after certain amount of time, and this n will be time, for example. So if the deviation from the initial separation grows exponentially, that means as long as this lambda is positive, then it's growing exponentially. Then it's a chaotic behavior. Okay. So so as long as lambda is positive, it's chaotic behavior. Here is a, and then we won't go through some analytically how to calculate, but mostly we calculate this numerical value. So here's the example of tent map. You calculate the one example which you can calculate analytically, but I don't think it is really showing much. But this graph 10.52 is the Lorentz exponents for the logistic map. So logistic map has one parameter r, so you can measure this lambda if it's and as function of lambda. So this is a numerical measure of computational lambda as a function of lambda. Now remember, between all the way up to 3 actually is it's simple periodic, and then at 3 is periodic doubling. So therefore is a finite set of attractor. Therefore this is a periodic, therefore lambda is less than 0, because it doesn't matter where you start, eventually you settle to those periodic orbit. But and it goes through you know, where is the point lambda, but it never get about 0 until you hit this 3.5. I forgot the limiting number. Until you hit this point, then you are entering chaotic regime, where the lambda become positive. And in the chaotic regime, you notice all this window of periodic, the window of periodic orbit. So, I mean, in fact, there are many of these things. In fact, you zoom in, there are many. There's, you know, this it's showing only few simply because the resolution of the graphic, Right? Now I have assignment. One assignment I think is essentially to create this. There's another one I think create a Lorentz exponent for different map. And when you look at those things, you find that the different map has a very similar behavior. So, and this is the point where we now start talking today, the topic today, which is on universality. So even though they are chaotic, there seems to be some genetic universal behavior among different maps. And this concept of universality, in fact, is a very physics-based concept, and it really came from study of the phase transition in physics problem. Now, how many of you know what phase transition in physics means? Anybody
like
know
between
what
states of matter?
Huh?
Like between states of matter?
Yes. So, for example, if you have a water, for example, water can be liquid, can be gas, and or can be ice. And temperature is a controlling parameter. So as you change a controlling parameter, you change from one phase to another. But you can have, for example, magnet. A magnet, for example, a ferromagnet. If you are at high temperature, it doesn't have a magnetic strength. But as you change the temperature, at certain temperature, what we call critical temperature, that magnet undergoing phase transition from non-magnetic to magnetic, so develop magnetization. That's another phase transition. Another example of phase transition, for example, is a material which we call superconductor. I briefly mentioned that some lecture back. A superconductor, again, as you change the temperature of a certain metal, usual metal, when you is conducting electricity, as a finite resistance. But my good dog is Lulu, no. Sorry, I got disrupted. Hey, behaving yourself, Lulu. So let me give you a treat. So as the temperature change is going from normal metal to superconductor, where the resistance goes to 0. So that's another phase transition. So physicists study many phase transition phenomena. What they found is that even though the system undergoing different transition has very different phenomena, the underlying physics, the underlying behavior of the system has a commonality, and they can describe that in terms of also called theory of phase transition. And so there are universality in this, and that's where the concept universality coming from. That actually can use the same theory to describe is seemingly very different system undergoing phase transition. So that's the concept universality. So here is a borrow from that concept universality. So we started logistic map, and here's another map which is called sign map. You all see this sign map? What I highlight? Hello?
Yeah.
Okay. Yeah. So if you start a sign map and they calculate Liouville, so sign map is look like this, right? You see the genetic shape is look very much like logistic map, right? Logistic map is qualitative. It also look like something like that, even though mathematics, the detail are different. And you can calculate studies dynamic. You find that this logistic maps undergoing similarly periodic doubling route to chaos. Namely, as you change the lambda, is from a simple periodic to period doubling and doubling again, and is undergoing very similar route to chaotic behavior. So qualitatively, the dynamics of two maps are identical. They both undergo periodic doubling route to chaos, and following by periodic window interwoven with chaotic band. So when you look at this what they call bifurcation diagram or orbit diagram, this is the one. The top one is a logistic map, which is we have shown in the class many times, and the bottom one is the sign map. Bottom one is sign map. So, well, no, I'm sorry, I take back. The top one is a sign map. The bottom one is a logistic map. So you can see qualitatively, they look very similar. You have periodic orbit and the doubling and the doubling and doubling and doubling, and then at a certain limit of R value, it becomes chaotic. And then in the general chaotic region, there are this window of periodic behavior. So this is a sign map, and this is a logistic map. You can see the biggest window here is a period 3, right? This is period 3, and the sign map also has the biggest window with a period 3. So even though the equation, mathematical equation, look very similar, different, but this genetic behavior period doubling to chaos are qualitatively essentially the same. In quantitatively, you have different value where it start to be doubling, where it get chaos, but qualitatively they are very similar. So this is what we call universality. So a lot of physics phenomenon, even though they look on the surface, it's a very different behavior, but the underlying structure mathematics has a very similarity. So that is the concept of similarity. Now, they both also go into talk about this U sequence, which I'm not going into in the detail. It had to do with, to say, if you look at actually how the orbit going from one side to another, it follows a certain particular sequence, and that sequence seems to be universal, even though for all the map they studied. So the U sequence has been found to experiment to be, and this U sequence not only in this toy model mathematics we studied, but in experiment they also found, for example, in chemical reaction following similar sequence, And this U sequence is qualitative, is started by Feigenbaum, and the Feigenbaum able to come up with some quantitative measure of universality. And this is related to this delta, this number called delta we earlier when we introduced, and that number eventually called Feigenbaum number. So let's look at that number a little bit quantitative. Let me just explain that. So quantitative measure of universality. So the history is to say around so Feigenbaum started this around 1975. So in terms of science, it is relatively modern. I personally have met Feigenbaum a couple of times during the conference. It's an interesting guy. So he started this since, and at the beginning, and remember back in 1975, the computation is very limited. So all he had is hand calculator, which basically he tried to iterate this map, and you can imagine there's no memory. You had to jot down every number you calculate and on the paper, and then try to do some analysis. So it's actually quite a tedious work. So Feigenbaum here in one of his paper, he recount what he studied. He spent a day trying to fit a conversion ratio. Now this conversion ratio, remember, is had to do referring to say this Rn value. Remember this Rn value? At certain value, period doubling, and then next value, period doubling again. The successive period doubling getting faster and faster. So Rn is a ratio of current period doubling of the R value to the next period doubling R value, the interval. So the ratio of those interval, and those ratio interval actually is approaches 4.669 something. So he did numerical calculation, and he found that is for logistic map, he found that is fit into seem to be very nicely into this geometric conversion. And then he remember somebody else mentioned that the period doubling behavior is also happened in this science map. And he thought, this is very different. He just did not study carefully. But then another month later, he come back to restudy this problem, and he find out that ratio, the period doubling behavior, this ratio also seems to be converged at a similar number. And in fact, that's where he has this epitome of a phase transition, analog to this concept universality. The phase transition, the theory of phase transition and the so-called renormalization group was heavily studied in the 60s and the 70s and 80s. So he was right in the midst of that development of this universality and the renormalization group, in fact. So that's what occurred to him, that the same conversion ratio appear, doesn't matter what a map is, as long as map qualitatively has its behavior called unimodular map. So basically, if this map function is something which has a hump, one hump, this is called unimodular. If something look like that, then that is you have same kind of a behavior, namely this delta, which is taking the ratio of the successive period doubling interval, is approaching a number which is same for every map. And this number now turned out to be a universal number. If the system undergoing periodic doubling route to chaos, that the successive interval behave very much exact the same number. So this number is a mysterious number. It's just like a pi, the number pi, which is the ratio of circumference to diameter, is a mysterious number. It's just an irrational number. Same thing like Euler's number is an irrational number. A square root 2, for example. The only problem is that this sigma cannot express in terms of known number. You cannot write down an expression in terms of known number. So this is a new one of those number which is showing up in nature, which is a irrational number. And in fact, there are experiments. There are people try to set up experiment to measure this number. The problem with measurement is, of course, it's very difficult. I mean, numerically, it's very easy to get higher accuracy, but they in actual experiment to get decent accuracy is kind of difficult. In fact, later I'll show the example. So this is in terms of scale, namely in terms of from this Rn, remember, is this point, this point, this point. It's a ratio of this interval to a success interval. It turned out not only on this R-axis there is a universality. If you do a certain measure of this, the width, the height of this individual interval, that scaling, the dn to dn plus 1, also has certain sense of universality. Namely, the scaling not only on the x-axis, on r-axis, scaling also has the same universality scaling on the x-axis, and that scaling it turned out to be a different number. So, alpha and the delta are universal. That's what Feigenbaum was able to show, and he developed a theory using renormalization group theory to actually did some analytical showing that there is some universality. He borrowed this from the normalization group analyzing statistics physics. Now, experimentally, there are people set up various experiments to try to verify indeed there is such universality. So there are different kind of experiments people set. One of the experiments which was very convincing is done by Lieber, and I also happen to know this guy. When I was a postdoc at the University of Chicago, he was on the faculty, the staff, and I remember his group studying all this turbulent phenomenon in convection phenomenon in various fluid and one of his well-known experiment is to measure this Feigenbaum number in study the convection of a mercury. And then, so the experiment is something look like this. If you have let's say imagine a liquid sitting in a box, and you heat it up at bottom uniformly, and so there's a temperature gradient between the top and the bottom. Now, if the temperature gradient is very small, then everything is steady. You see this, the temperature simply changes from bottom to top, now as you increase the temperature gradient, you start to see convection develop. Namely, there is low structure where you see this the fluid start circulating. So the hot fluid is moving up to the top, and then it dissipates the heat, and then it's moved on the other side coming down. So the cold fluid moving down and again the heat, and that's how the heat continually dissipate from the bottom to the top. And by controlling where it's set up, he was able to study the periodic behavior. Namely, he was setting up using particular mercury, I think, and then apply a magnetic field in this direction, so able to make this low steady state. And then what he found that is basically at a certain controlling parameter, I think controlling parameter used was a Reynolds number to control it. You see this phenomenon that originally this looked like uniform row break into oscillating behavior. And by measuring the temperature at a particular point, he found the following. For example, this is a this is a time, and this is a different Reynolds number and if, at this particular random number, for example, you have simple periodic behavior. As you increase this random number, and you can see this period doubling happens, and then periodic tripling happens. So he was able to measure this controlling parameter when period doubling and the doubling again happen, and from that he can deduce this ratio of this successive period doubling. So you get something number like 4.4 plus minus 1. So which is very close, at least close in 2 digits to the theoretical value. The problem is to get the higher value, higher accuracy is, as I said earlier, this, every time you get one, in order to get 1 more digit, you need a 5-fold increase in experiment accuracy, because this thing is decreasing by this ratio for almost 5. So that's what makes it difficult to actually do very accurate measurement. So here's a summary of various experiment: water, mercury, or electronic diode circuit instability, Joseph junction, which is a simple conductivity. They try to simulate this chaotic behavior, and the measurement, experimental measurement, actually all within certain uncertainty, same as a theoretical value. So now by then it's pretty well. By the 80s, it's pretty well established. People accept that there is indeed a universality in this period doubling route to chaos. So that's the experiment aside. Now, so the question is, that's really had something to do with the science. In fact, so the question one naturally may ask to say, this map we're starting is discrete. How actually it's relate to the continuous time system, where in all the experiment system, it's not discrete, it's actually continuous time evolution, but rather than discrete. So the way you can think about it is to say, for example, this actual experiment, measurement of the temperature at a certain point as function of time. Imagine you take a slice going through here. They take a slice from here, for example. Or you say, you look at the maximum value of the peak temperature. So in this parameter, the peak temperature is just same value. So therefore, it's taking up to a certain time, come back to peak value. Now you should remind you somewhere back in 2 chapters back when we talked about Lorentz Chapter, we developed a so-called Lorentz Map to study how Lorentz Chapter behavior. Namely, we examine the maximum value of this time series. So you can see in this case, maximum value, given this maximum value, there is a next maximum value coming back is identical. But as you change the controlling parameter, this maximum at certain controlling parameter, this maximum value now has 2. So you can see it's oscillating back and forward between these 2. So this is how you actually relate the continuous variable system, the real system, to the discrete system. You take a slice through this attractor and examine the periodic behavior, how is it come back to the same region. So another way to look at it is, here is a simple continuous 3-dimensional system called Lossless System, which has x, y, z, and it has a very simple term. Everything is linear except this term z times x. So there is a nonlinear term here. And if you now study this as a function of ABC as a parameter, you find that at certain parameter, for example, like c equal to 2.5, and here I think you fix a and b, and you plot this x and the y. In long-term behavior, it's a simple periodic object. All right, it's a simple periodic orbit. You can see it's periodic. So therefore, if you take a slide, for example, you know, if you can take a slide going through this, since like in this point, take a slide going through here, that is always come back to the same value after a certain time. You can think about that as a map, that given the fact that at this time it's here, after a certain time you come back to the same place. So that is a mapping behavior. Now as you change the C value from 2.5 to 3.5, you find this original periodic orbit is become periodic doubling. So therefore, if you take a slice here, going through there, you find now there are two values. So first time is going this value, the second time go back this value, and then go back. So in fact, you see this period doubling behavior. This is essentially, so from initial one period, you need two period, it's no longer period, you need a 2 time scale to come back to the same period, to come back to the same point. So that's this periodic doubling behavior. And as you keep changing that, you see that from periodic to periodic doubling, and then to doubling again, and then eventually to chaotic regime. Now, notice that this behavior in the continuous case has to happen in 3 dimensions. You cannot have this behavior in 2 dimensions. Any of you notice why you cannot have this kind of things behavior in 2 dimensions? You remember that?
Trajectories can't cross.
Yeah, trajectories can cross, right. So if this is 2-dimension system, then actually trajectory cross here. So that is not allowed. In 3 dimensions, this trajectory actually never cross because the z-axis is different in this loop and in this loop. Right. So you can think about a loop you know, you can make well, I think you take a string, you can easily imagine the z value for this loop is different from that loop. Right. So that's why the chaotic behavior has to have a 3-dimension system. The minimum dimension system to have chaotic behavior in continuous system is a 3-dimension. So you have this. So therefore, this just to show that in fact you know, the relationship between this map we are starting, this 1D, it look like very simple 1D map, how it may relate to continuous variable system in 3 dimensions, and same behavior of a chaotic behavior that is happening. Now, so period doubling bifurcation is happening in this system too. And in fact, if you do a Lorentz map essentially is to plot, you know, plot the successful maximum point, in, let's say in y value, for example, as iterate. And in fact, you look at that, you basically the maximum value in the n plus 1 was maximum value in n's. In fact, is chasing out a mapping which is unimodular. You see, it's unimodular, qualitatively unimodular. That unimodule has the same behavior as the logistic map. That's why the underlying periodic doubling behavior is in fact is universal. So that's what they underline. And in fact, you can study this lossless system, and they, you know, and create this orbit diagram, a bifurcation diagram. So C is the controlling parameter, and X is the max. Is our label of in terms of mapping, namely Lorentz mapping. So you can see at a certain value, it period doubling, and then period doubling again, and then it transition to chaos. As it transition to chaos, in the chaos region, there again there are window of a period behavior. In fact, you see the largest window also is a period 3. So it's just like a logistic map and a like sign map. So this qualitative behavior seems to be very much universal, very much more. So this orbit diagram allows us to keep track of the bifurcation. In lossless system, we see the period doubling log to chaos, and the larger 3 window is all similar. And So, and if you, some of you may be interested, you know, you can just slightly modify how we, you know, this Lorentz equation solution, and how we create a bifurcation map. Maybe you can create this map, for example. Create this bifurcation diagram for lossless equation. No. So one caution to say, the theory we describe, and then we have handle on the chaotic behavior, and this chaotic behavior, what you call mild chaotic system. So we can develop theory. Now, in nature, a much more complex chaotic behavior, in particular, the turbulent phenomenon is the area which is still very much unresolved. Namely, there's still no mathematical structure which one can come up to describe fully turbulent system in fluid flow. You know, you see the eddy develop in the turbulent system, like for example, your toilet when you flush it, or your sink when you turn on the grinder, for example. You see it, or you see the eddy in the creek, for example, or in the river flow. Those are still very much difficult to describe in terms of genetic, more general mathematical structure. So so that is now this all is a system where we describe this mild behavior, can be to a certain degree analytically analyzed in terms of the normalization analysis. And this section is a little bit heavy in math, so we're going to skip this section. But some of you might be interested in, you can read through. So we're going to skip the normalization analysis. It's basic mathematical analytical analysis of this cycle and the period doubling behavior. So that is kind of wrap up our study of the map, 1D map, and the quantitative measure of chaos. And one interesting aspect of things which I'd like to emphasize, which give us a natural transition to that chapter, is you notice this a bifurcation map which we done earlier, and in fact let me now switch to the Jupyter lab. So this bifurcation diagram, right? If I zoom in a small region of this, which I think I did here. So if I zoom in a small region of this, this is, well, this, okay, let me zoom in this in different region. So it's 3.8, 3.9, between 3.4, 4, 6. See. No kernel. What's happening? Okay, I need to restart the kernel. They run this again. Take a minute or two because this is a large map. How long last time it take to run? I forgot. Looked like it take longer than I expected. Think it's something gets stuck. Did the last time take this long? Oh, it's here, right? I don't know what. Sometimes it's showing up as inline, sometimes does not. I don't know when showing up as inline, when it's not.
Maybe when you restarted the kernel, the magic line to make it inline wasn't run.
Oh, I see.
So it just outputted the image somewhere else instead of in the notebook.
Oh, okay. So you think I didn't have this magic line?
So if you ran the entire notebook, then it should.
So I should have
inline.
this. Maybe put here. Maybe on this. Okay. That's it, showing up. No, this is not what I want. I wanted this one. Well, it's still showing up. So I probably need to start from the very beginning, but I don't want to do it. But you can kind of, this is actually nice. So now I can see. So this is our original behavior, original map, bifurcation map between, the only thing is the exit is not showing up. So this is between, I think, all the way to 4. So what I did is I zoom in this green region, and that is what this look like, right? So you can see, oh, is now doing the twice. So you can see that the qualitatively this period doubling behavior is repeat itself here, okay? And in fact, if you zoom in this tiny region again, well, zooming this region, I get this. If you zoom in this region, you see it's repeating itself. It's repeating itself. You see, there is also a larger window here, and there's a period doubling. So this is something what we call self-similarity. Namely, an object, when I look at the smaller scale, is repeat itself. Now sometimes it's repeat itself exactly, sometimes it just say approximately repeat itself, namely genetic. So, and this is something we call self-similarity. And this gives us a handle to make a transition to a new object called fractal. And so we're going to devote a next chapter to talk about the fractal behavior. So now I'm going back to, so that I can close this. To look at the now, so we are going to, let me just close all this because, okay. So that's what I say. If you zooming in, you get qualitative similar behavior, and that's something what to call self-similarity. And the self-similarity is a genetic property of the object called fractal. So this leads us to now to a new chapter of fractal. And so let me do a little bit. I want to okay, so okay, So now we move to chapter 11 on fractal. All right, fractal.